induction. I'm going to put a exclamation, exclamation, exclamation. Okay. So, two important ingredients in an induction problem. The first is that you're trying to prove something for all n. So just like we were trying to prove for the postage machine, we were trying to prove that you can make whatever postage you want for all n. Well, not quite for all n. We were saying for all n bigger than or equal to 24. Okay, so you're trying to prove something for all n. Okay, let's say, greater than or equal to something. Let's say greater than or equal to 1. It could be 24, greater than or equal to 24, greater than or equal to 1, greater than or equal to 10. Okay, what you're trying to make it for in terms of the lower bound for n is not so important. The important part is you're trying to make it for all n. Okay, greater than or equal to 1 is the typical type of an induction. Okay, so you're trying to prove something for all n, and the starting point is, for any induction is a predicate. You're trying to prove what? So there's something. Okay, so you have a predicate. Okay, so what is a predicate? So P of n. So this is, remember what a predicate does. It returns a statement. So this is a claim that depends on n. Okay, so you're asserting that this predicate is true for all n greater equal to 1. So you have a predicate P of n. Okay. And this property, this predicate that returns a claim for n is what you're trying to prove for all n. Okay. So let's look at some examples. Okay. So I'm going to list the example P of n, and then I'm going to list the claim that we're trying to prove. So, predicate, and then the claim. So what's the predicate? So P of n, okay, is the claim. Postage of n can be made with 5 and 7 cent stamps. Okay. That's a perfectly valid claim. Okay. It's a claim that takes as input n, okay, and outputs a statement, and that statement can either be true or false. Okay. You can't argue with it that it can be either true or false. Okay. And what's the claim that I'm trying to make here? The claim that I'm trying to make and essentially proved when we discuss this example is that, for all n greater equal to 24, I'm going to assert P of n as true. And it's important, it's for all n. Okay, here's another predicate. So let's call this 1. Predicate number 2. Okay, P of n, okay, is the statement, it's the claim that n squared minus n plus 41 is prime. Okay, that's a claim. So what's P of 1? P of 1 claims that 1 minus 1 plus 41, which is 41, is prime. That's true. Okay. And what's the claim I'm trying to make here? The claim I'm trying to make is that for all n greater than or equal to 1, in this case, I'm going to assert that P of n is true. P of n. So for all n greater than or equal to 1, okay, I'm asserting the claim P of n to be true. Now, when you look at my 2 criteria for induction to be, a plausible approach, you will see that I'm trying to prove something for all. Here's the for all. Well, we in this case for all n bigger than or equal to 24. In this case for all n bigger than or equal to 1. So, but there's a for all. Okay. And we have a predicate. P of n. Okay. Here's another example. Okay, P of n. 4 raised to the power n minus 1 is divisible by 3. Wow, it's a predicate. Okay, it says input n and produces a claim, a statement. Okay, so for example, when n equals 1, P of 1 says, okay, that 4 to the power 1, which is 4 minus 1, which is 3, so 3 is divisible by 3, clearly true. Okay, and what's the claim I'm making? I'm going to assert that P of n is true for all n greater equal to 1. P of n is true for all n greater equal to 1. I'm going to assert P of n as true. Okay. Now, it's fine to assert claims. I can assert whatever I want. Okay. The only question is whether it's true. And that's what we are going to try to establish by proving the claim. And the method of proof is induction. Okay. But let's first see, why do we need induction? Okay. So the first thing you do, so we already looked at this claim. So let's look at the other two claims. The first thing you do is to see, at least, for small values of n, are the two claims correct? Tinker. Tinker. So let's consider, in both of these cases, we are interested in n greater or equal to 1. Okay, so let's tinker with n, taking on various values, and we'll start at 1, and we'll go up 2, 3, 4, 5, 6, 7. Wow, we're energetic. Okay, so we'll go up to 8. Okay, and I'm going to look at, n squared minus n plus 41, n squared minus n plus 41, and I'm going to look at 4 to the n minus 1. Okay, or more specifically, let me look at 4 to the n minus 1 divided by 3. Why divided by 3? Because I'm interested in whether it's divisible by 3. So if 4 to the n minus 1 divided by 3 is an integer, then 4 to the n minus 1 is divisible by 3, and that claim is true. Okay, so let's tinker. Let's do these examples. Now I'm going to emphasize that when it comes to induction and in general math, tinkering is absolutely essential. Okay. So when n is 1, we already got that this is 41, and 4 to the n minus 1 divided by 3 is 1. Okay, but let's go for higher values. So 4 minus 1 is 3 plus 40. 2 squared minus 1 is 2 squared minus 2 is 4 minus 2 plus 41, which is 43. Okay, that's prime. 3 squared minus 3 is plus 41 is 47, and if you plug in 4, you get 53, and if you plug in 5, you get 61, and then you'll get 71 and 83, and you'll even get 97 here. And if you want, you can go and check that all of these are prime. So they're all prime as expected from P of n. Okay, so if we're claiming P of n is true for all n bigger than or equal to 1, well, it had better be true for at least the first 8n. So it's true, 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 true. Okay. Let's look at 4 to the n minus 1 divided by 3. When n equals 2, we have 15 over 3, so we have 5. When n equals 3, we have 4 cubed minus 1, so we have 64 minus 1 divided by 3, which is 21. Notice it's an integer. We have 85. You can compute these numbers. We have 341. We have 1365, we have 5461, and we have 845. Okay, so 4 to the power n minus 1 over 3, always an integer. So check, 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 check. N squared minus n plus 41, always prime. So it looks like we're ready. Okay, so we argued that, okay, this may have been proved, and I gave you the intuition for why. It looks like we're ready to believe this claim, and we're ready to believe this claim. Why? Based on tinkering. Okay. So now I want to emphasize the big flaw. Okay. Tinkering is never a proof. Never. Okay. And let's keep going. And this is why we need induction. We need a rigorous proof. Okay. If you keep going, if you come up to 41, dot, 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 dot. If you come up to 41, so n equals 41, look, here you'll have 41 squared minus 41 plus 41. Okay. So you'll have 41 squared. And that's clearly not a prime. And this is the danger with tinkering when it comes to for all. Okay. For all means for all. Tinkering only shows that it's true for some. Okay? And if you stop your tinkering when you get tired, having shown it for some, you cannot conclude for all. Okay? Because maybe later on, okay, it's going to be false, just like here. And, another way of putting that is, okay, you verified it for 8, but then you ask yourself the question, am I sure it's true for all? Let me check 9. 9 is true. Oh, am I sure it's true? Let me check 10. And that's going to happen in this case. So we might say, well, we need to, verifying up to 8 is not enough. Is verifying up to 41 enough? No, because even 41 is for some, not for all. So here we would verify, okay, good. Then we would check 9, good. Then we would check 10, good. And then we say, can I stop? Oh, what about 11? Oh, okay, let's check 11, good. Let's check 12, good. Okay, can I stop? Oh, what about 13? So check 13, So tinkering and checking / verifying the claim for some n is never a proof for all n. Okay, it gives you a hint that, this may or may not be true. Okay, but it's sort of an inconclusive hint. When it's true for all up to some value, at least you haven't disproved the claim. But in this case, we disproved it, so we can say, oh, that's false. Okay. Now, how high do we have to go to convince ourselves of this claim? Well, there's no how high, because no matter how high you go, it's still for some, whatever that high value is. Okay. So we need induction, because in order to prove for all, there's no amount of tinkering / verifying that will suffice, because you always have this doubt that the next one will fail. Okay. So what we're going to do, I'm going to go step by step through the proof of this guy using induction. Okay. And that's the best way to learn induction, to see and do example after example after example. Okay. So let me erase the board, and then we will prove this guy. Okay. For all n. And there will be no doubt that it is true for all n.